Okay, we start up again. I finally found some old exams, so I put out on the homepage for you, so you can have a peek. And you see here the turbulent problem from 2015, I think it was. The important part, that's sort of the part of the turbulence that we covered the last time, the modeling part. Transport equations, full Reynolds stress model, what's the meaning of the different terms, yada yada yada. But also some question here about DNS, large eddy simulations. But you see the style of the exam is not difficult. It's more a sort of a checkpoint. Have you seen this? Have you heard about this? Do you know what this is? So it's fairly easy to actually pass the exam, so you shouldn't worry too much about it. But now at least you have some old exams you can have a look at, and I will follow the same style, I think. Shouldn't be any major differences there. And I haven't heard any objections to our suggested exam date, May 27th. So I will try to push that one into the exam office and see what happens. We may get it, or we may get a totally different date. We don't know, but at least we can try to influence them. Okay, any administrative questions while we're at it? No? Let us go to turbulence. This is the final article in this turbulence part 2 that you have been given. And then this actually is given in a mathematical journal. But for us, it's something quite okay, actually. It's the same problem case that we had earlier. It's the same simulation. So DNS of the flow between two parallel plates, and here mathematicians, they don't use x, y, and z. They use x1 and x2 and so on. So we have to rewrite the article a little bit. So here you have the problem. Equation of motion, you have continuity, and then you have the non-dimensional Navier-Stokes momentum equation. So you have 1 over the Reynolds number. And yes, possible to also define the Reynolds number using this skin friction velocity if you want to do that. So here it's a question now of obtaining good statistical results. So here we are sort of focusing on the sampling procedure. As I said, we have in BASIC a one-dimensional problem. So you have functions varying from wall to wall. So you can take average for every plane. So that's one way of averaging. But to get good statistics, you also need averaging in time as well. So you are talking about obtaining a good ensemble, as you call it, a whole bunch of solutions, and then create a good average. And the more members in the ensemble that you have, the better the statistics will be. Now the problem is, what quantities are you looking at? So here, sort of a little calculation here. If you want the first order statistics, meaning the velocity, the average velocity. If it's the intensities, that's velocity fluctuating squared. If it's the third momentum, as we call it, velocity fluctuating to the power of 3 or power of 4 and so on. The higher the power, the more the bigger ensemble you need. Now this picture, that is the flow, a snapshot of the flow, the solution for a plate fairly close to the wall. So the problem, flow between two parallel plates, the velocity field, something like this on average. So you have a plate somewhere down here. So all conditions should be equal inside this plane. The variation that we are interested in the end, that is here in and out of the paper plane. Here it's plotted the streamwise velocity here, but then I have subtracted the average velocity. So here the solid lines will be a region where the streamwise velocity is bigger than the average. The dashed areas where they are smaller than the average velocity. If you look at the structure, first of all, it's sort of quite streaky. It's elongated in the streamwise direction. So you have these turbulent streaks close to a wall, and they can be pretty long. This is the entire domain. And I believe my domain was some 4,000 plus units or so in the streamwise direction. So you see they can be pretty long. In the spanwise direction, here would then be in and out of the paper plane. I didn't have that many units to do, I think around 2,000 or so. Now, if you look at the structure here, remember I have cyclic boundary conditions. So whatever goes out here, you should find entering on the other side. And also, whatever goes up here should enter down here. So they are sort of coupled in both x direction and y direction. Cyclic boundary conditions. Because, I mean, you have no option. How else should you find a complete, fully developed, correct, correlated inlet velocity that is turbulent? You can't get it. So you have to use this cyclic boundary conditions in order to achieve a simulation at all. Or else you need a very, 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 very long channel. Extremely long. So just forget it. Then you might argue, then this is pretty worthless, isn't it? If you have now, say, a more complex problem, you have, say, something like this, flow over a backward-facing step, for instance. Now what? Well, you will have this zone here, of course, and then the outlet here, and then the inlet here. How can you simulate that one with the DNS? Well, you can't use periodic boundary conditions. You can't patch whatever goes out here and send it in again. There are two different simulations, two different solutions. So what do? You can do the following. You take just a simple simulation, flow between two parallel plates, and let this simulation run by itself. And then on a cross section here, you pick velocities and pressure, and then you use those for this simulation as an inlet. That's possible. For the outlet, there you have no idea. So there you typically would use some Neumann condition or something, derivative equal to 0. It will be in adder, but hopefully that adder shouldn't propagate too far upstream. So you should have decent results here in the end. So that's one way around this problem, finding input values for a fully developed turbulent flow. This streaky structure that the turbulence have, that's also something you now have to pay attention to when you define your area. I mean, the distance from wall to wall, that's of course something you choose, but then you need to choose a length and then even a width into the z direction as well. How big should they be? Well, they have to be so big that these elongated structures don't go straight through the entire domain because of the cyclic boundary conditions. So if you have then one streaky structure that is so long that it goes straight through the entire channel, he will sort of sustain himself and be enhanced unphysically. So these streaky structures, they are typically no more than, say, 1,000 plus units, but that means you need a domain that is at least 2,000, and here I had 4, so it was okay. Also, from side to side, I mean, you have to define a depth here, and then you need space, so you have several of these positive and negative streaks side by side. And here you see I have quite adequate space, so here the domain should be big enough. Back to the sampling procedures. So here sort of I try to calculate what will the error be depending on what quantity you are interested in. To get the average velocity profile, that's not so hard. You can find that one fairly quick. You don't need that many samples. When you look upon these quantities, you need more. And then you see if you need this one to the power of 3 or 4 or even higher, we are going to need many, many samples. So the error will increase quite rapidly. So the higher order, the more samples you are going to need if you want it correctly. So it can be very expensive if you're really interested in these higher order quantities. Why should we be interested in them? Well, we are actually interested in them, not as a solution for this problem. Then you say you have the average velocity, then you know everything, and pressure. But to help these poor guys that are dealing with turbulence models. Inside a turbulence model, they will typically use these quantities here, or even the fourth order. So for the guys dealing with turbulence models, they will be very interested in to see how these quantities actually, what they actually look like. So that was the argument. Yeah, single point correlations, not so interested in. Second moments, yes, they are of course interesting. And here you see the shear stress. When you do the calculation here, I think I mentioned it, when you had the cuvette flow, he is moving with a constant velocity, then you had a velocity profile that went something like this, sort of an S-shaped velocity profile. And here, if you plot the total shear, that is the viscous, the U, what was it there? It was a Z, I think. The viscous shear, and then you add also the turbulent, UV. For the cuvette flow, you should get a straight line. That's how far you can get with the analytical simulation. For this problem, when you do the same, from wall to wall, then you should get a line that goes from +1 to -1. And that is what I have tried to draw here. So the dashed line, that is actually then the sum of the viscous and the turbulent shear. So, I mean, you can try to set up the Navier-Stokes, simplify it with the Ransey equations and see how far you can get. Then you can see that, okay, the total shear has to be a straight line, and for a cuvette, yes, it had to be constant. This to be used as a control also. that you have correct or adequate statistics. So here are some of the results. The intensities, U square, V square, W square, compared with some experiments. And yeah, well, it doesn't look too bad actually. Some of these experiments little higher in value, but still we speak the same language at least. And then you come to the nice thing about the DNS. You know everything. Instead of into the lab, when you want to look at things like this, pressure and velocity correlations, how these quantities actually look like, they are impossible to measure in the lab. You can't measure pressure and velocity in the same point. A pressure measurement, he will require a probe of some kind that will destroy the velocity field. So these are not possible to find experimentally. At least nobody has done it yet. But with the DNS, you know everything. So here actually I have the behavior of these quantities. So then the experimentalists can sort of look upon it with NVIs. Yeah, different higher order terms. You have 3 turbulent velocities and then time averaged. And here the experimentalists have problems, very hard to calculate these correctly. As you can see, they have a problem. Somebody has fired a shotgun almost. And you can even go to the 4th order. It's very, very hard to get that one correct. Here actually I think it was the Swedes, Ref 3, that did a very good job here. Yeah, I think they used laser Doppler, while the circles, Ref 10, should be from Japan, where they used PIV techniques. You send in a lot of fluid markers, particles into the flow, then you set up 3 or more video cameras, and from the videos you identify each particle, and then you trace him in space and time, and then you do calculations of the different quantities out of that. Very hard. I think they used just about as much CPU as I did on the DNS, just to do the calculations. Yeah, skewness and flatness, they are the 3rd order, but then scaled against the 2nd order. Very touchy quantities, especially when you get close to the walls. Very hard to measure and calculate correctly. And here, flatness, that's the 4th order. Very hard to get correct. The particle tracking, they have problems when you're getting very, very close to the wall. The particles will bang into the wall, so you will have error in the measurements there. Laser, that would be better getting closer to the wall. So you see the Swedes here, they are getting more or less correct results. Yeah, here we have the definition of skewness and flatness. 3rd and 4th order moments. For the turbulence modelers, people who are creating turbulence models, I mean, they were really happy when we started doing DNS and could then provide them with actual numbers. How does these functions actually look like? Remember, for a full Reynolds stress model, if you can recall, transport equation for all of the different Reynolds stresses, it was only the production term, this one, that was correct. There you don't have to model anything. You have already the unknown mean velocity field, the gradients there, and the Reynolds stresses themselves, well, they are also unknown functions. So the production term, he didn't need any modeling. But all the other terms, they needed modeling. The pressure strain term, this redistribution term that could exchange energy between the different Reynolds stress components. Impossible to measure in the lab. Pressure fluctuations multiplied with velocity fluctuating gradients. Thank you very much. Very hard to get. But with the DNS, no problem. Here the diffusion terms have been split into 3 parts. The triple correlations, and then some gradients with pressure and velocity, and finally a viscous term as well. And finally here the different dissipations. I mean, all these has to be modeled, and for a turbulence modeler can be very hard to get this one correct. But with the DNS, no problem, we have everything. And if you want to see how they look, then as an example here, I set up the total budget for one component, just picked one. And this equation now is analytically perfect. As we discussed, when you do the Reynolds averaging with the Navier-Stokes, you can manipulate the equations and find transport equations for whatever you want. So this is then a transport equation for one of these Reynolds stresses. And you have the analytical expressions listed here. Just insert for one of them. Now, the rate of change is 0. We have a steady state problem. So that one is 0. So we know the sort of the answer. If you add all these together, you should get 0. So fairly easy to check. Here you have one of the diffusion terms. That was involving pressure, so we don't have any experiments to compare with. Here also the redistribution terms. Very hard to measure in the lab, actually impossible. So again, not so easy to have anything to compare with. You see the behavior is quite complex, and here you have the plus unit scale, so you see a lot of action is taking place quite close to the wall, inside this viscous sublayer, not to be confused with a laminar sublayer, absolutely not laminar. Now this one was a little cute. If you can recall from the Reynolds stress model, we should actually have used 1 epsilon, 1 dissipation, for each of the different Reynolds stress components. So they should have their own private epsilon. People don't do that. We say, let's make it simple. We just use the same epsilon for all of them. But actually, the epsilon has quite different behavior. So epsilon 1,1 is quite different from 2,2 and 3,3 and so on. But to create an average, well, yes, that's possible. Here, they have actually some experimental data, but they haven't measured it. What they have done is to try to measure as many terms as possible, and then try to add up and say that, okay, we know we should have 0, but then we have something that's called the rest, and then they say the rest has to be epsilon. That's one way to do it. Anyway, the sort of the average, if you take 1/2 of the sum of these, you have this big dashed line here. And this is now a non-dimensional version of it. And turbulence modelers, they believed strongly that on the wall itself, the epsilon is not 0. He should start with 0.1, and then he should go up to roughly 0.2, and then he should level off inside your computational domain. That was the behavior that everybody believed that the dissipation should have. And the modelers, they were really struggling to achieve just this behavior. And you can still find turbulence models that will obtain this behavior for the epsilon. But it's totally wrong. You can see that he actually peaks on the wall. That's the biggest value, 0.2, and then he drops down. So that was sort of a big surprise for the turbulence modelers when they saw this for the first time. So the epsilon, they had got it completely wrong actually. But how could they know? It was a very hard quantity to find. But with the DNS, now we know everything, so not a problem. And here, finally, you take the entire budget. You take all of these quantities and you add them together. And here, the dashed line in the center is actually not the zero line, it's the sum of all terms. And yes, it is indeed a straight line. Meaning, okay, then you have fulfilled the equation, you have solved it correctly. Because you know it should be zero. And indeed it is. But also look at the behavior inside y plus equals 10. It's quite violently behavior, quite big changes, quite hard gradients. So a lot of action is taking place inside this viscous sublayer. Of course, then it's very important to resolve that one correctly to get good results. 2-point velocity correlations, that is something also we should have a peek into. What is a 2-point correlation? Well, if you can recall this image that we had with these streaky structures. So here you had one region with high speed, here you had another region with low speed, and so on side by side, quite elongated. Now a 2-point correlation, as you can see from the definition there, you take one velocity in one single point, say for instance here, take the velocity at that point, and then you multiply him with a velocity at a certain distance, this point for instance. So here you will now have sort of a distance between those two, and of course if this distance is 0, then you just have the velocity squared. But if you start increasing this distance, then they will be more and more uncorrelated. If they are very close to each other, they will normally talk to each other quite strongly. So the correlation should then start, you non-dimensionalize it, so you should start with 1, and then he should drop quite rapidly when you start going here in the streamwise direction. But you have to go pretty far before he goes all the way down to 0, say 1,000 plus units, maybe even longer. So that will now be the correlation in the streamwise direction with the velocity in the streamwise direction. Then you can create a correlation with the velocity in that direction, but the deltas you are looking at will be in that direction. How will that correlation look like? Well, you always start with 1, but here quite rapidly you will go negative. So he will start here and then go negative before he goes to 0. That should be the expected behavior for him. And indeed, that is what you get. So to the left, you will there have the correlation, the streamwise velocity in the streamwise direction. Then you will have a correlation looking something like this. And indeed, we do. For the, say, the cross-stream direction here, it's still the streamwise velocities, but now how do they correlate in this direction? See, they go negative quite rapidly. So here, the experimentalists are actually good, decent job, I would say, because it's not easy to measure several points at the same time. With a laser, okay, how many lasers do you have? And so it's quite expensive. For the Japanese people here dealing with particle tracking and velocimetry, they had it more easy, of course. But then they had trouble finding correct correlations very close to the wall. What we were interested in here was this average distance between these elongated structures, these streaky structures. What's the average distance between these two? And it should be around 100 plus units. So very close to the wall, around 100, looks actually quite okay, and compare quite favorably also with the experiments. Some continuing here with the correlations. I can remove this one. If you take a Fourier transform of your two-point correlations, then you get what is called an energy spectra. So that's something we should talk about. Turbulent energy spectra. So here you have an energy, and then you take it as a function of a wave number. A wave number, you can think of it as 1 over delta distance, something like that. So it's sort of the reciprocal of your distance in space. Make an energy spectra of the ocean on the planet. So the biggest scales that we operate with, when you look at the ocean, that will be of the length scale of some 100 kilometers. So you have the Gulf Stream, some strong current in the ocean. They will be one source of energy into the ocean. So the first peak you will have will now be on a length scale, say 100 kilometers or something. Quite a big peak there. And he will push energy into the ocean. Then you'll find another peak. Then you are talking a length scale of, say, 1 kilometer. Then we are talking tidal waves, in and out of fjords, stuff like that. That's also a source of energy into the ocean. And then the energy will decay, and then we get another peak. Now we are talking waves, surface waves from the wind. That's a scale around 10 meters. And from then on, the energy should drop. Unless you have some fish, small fish, then you might get a little peak here, okay? That's your problem, wasn't it? So typically an energy spectra will look something like that. And here you have, it's a log-log plot, so the energy will drop several decades. And in the end, 0, of course. And here, the smallest length scale, Kolmogorov. Then you don't have any energy left. Then it's just viscosity, friction. So we would assume for the ocean an energy spectrum looking something like this. What about these two-point correlations here? Well, if you do a Fourier composition here, the biggest energy you get here with the say the streamwise correlations will be then that you have one wave that is infinitely long. So from that first figure, I would assume an energy spectrum with the biggest energy where you have infinitely long waves. So he should go something like this from him. This one, he has something that goes negative. So the biggest energy here will be when you have a cosine wave that will match him perfectly. So this guy, he will have an energy spectrum looking something like this. So he will peak just when you have that Fourier mode that matches this positive-negative correlation. These energy spectra, they can be also a valid aid with the DNS. When you plot them, you should get your Kolmogorov scale here. I mean, that should be your finest mesh, of course, the smallest delta X or delta Y or whatever that you have. Then you have resolved everything. So if you get an energy spectra that sort of drops many, many decades, should be several, 6, 7 decades, then you don't have any energy left, then you have resolved absolutely the major part of the energy. Of course, the important part for the flow, that's where you have a lot of energy. And of course, that will be the big scale in your problem, but to resolve it decently, then you also need to resolve sort of the small scale behavior here as well. If you don't have an adequate mesh, if your cell size, the smallest cells, they are too big, then you will risk having an energy spectrum going something like this, or even something like this. That's a little hint. Pay more memory, use more cells. This is not good. It's not supposed to go up again or flatten out. So you could use these energy spectra to test your DNS. How good is it? Is it adequate? Have you enough cells? What we now are cheating with as a possibility is to say that I can't afford the full Kolmogorov resolution. I can't find all all the turbulent scales all the way down to Kolmogorov. So I say I stop here somewhere. I can't really do everything, but I get the broad part. I get the large eddy simulation here. And that should be sort of most of the activity, most of the turbulent motion. Yes, I can cover that one with my simulation. But I have to do something with the rest. I'm missing this part. And if you just ignore it, then you will see your energy spectra, they will either start to go here or even go up again. Then you don't have enough resolution. So what do? You put in a subgrid scale model. So to cover this part, so here is your smallest delta X or delta Y or whatever. That's your grid size. Or actually, it's reciprocal, so it's 1 over. And even smaller scales, you use a subgrid scale turbulence model to cover this part. Subgrid scale turbulence model. And there you use a very, very simple model like Prandtl's mixing layer or not a transport equation, just an algebraic turbulence model. Very, very easy. But remember, in the end, yes, you can cheat. You could use this subgrid scale turbulence model to cover for the activity inside your computational cells. Yes, you can do that. And they have even been playing around now with what they call very large eddy simulation and then very, very large eddy simulation and so on. They're pushing the limit. And yes, it works. So they can actually do a fairly decent large eddy simulation now with quite high Reynolds number, but it's expensive, very expensive indeed. But in order to get good results, remember the nature of turbulence. It's three-dimensional, it's transient. So you still, with LAS, have to use full three-dimensional codes, and it must be transient as well. I have to flip this one. Here is a figure from the end of the 80s, roughly. And the future actually looked quite bright. We had the supercomputers in those days, the Cray machines, and others as well, that looked quite promising. So here in this plot, you see the speed of the computers. Here in flops, as floating point operations per second. And the y-axis here is memory, given in what we call words. One word was 8 bytes. So we were playing around with different Cray machines. The first one we bought here in Trondheim, that was the XMP. And then later we bought a YMP machine. We were smelling on a Cray 2 machine, but they were too expensive. So the simulation I did was actually on a Cray 2 machine that was located then in Switzerland. There were only 3 on the planet at the time. So the simulation I did, that was actually the biggest simulation with finite difference at the time in the world. So that was fun. But it was expensive. I spent 9 months doing that simulation, so it was heavy. And now you can do it on a laptop. It's embarrassing. But still, this scale, I mean, it's a log scale. So how big machines do you have today? Well, we had sort of hoped that this would sort of continue, that the speed of the CPUs should increase, and also the memory should be cheaper and cheaper. And true, yes, they have been. But look at what you can do. So the simplest one, just between 2 plates or a switch channel or something like that. Then a full Navier-Stokes solution, DNS, that's in this range down here. So we sort of just could do it, slightly turbulent, the Reynolds number very, very low. If you look at, say, the flow around an entire aircraft, a full DNS, you are somewhere up here. And we don't have this much amount of memory on the planet yet, nor do we have exaflops. We are getting there, but it takes time. And I'm not sure that we will ever get there. I'm not certain that the computers are going to be big and fast enough to even do something like that. But of course, they are getting bigger and bigger, not because one CPU is faster, but you have plenty of CPUs now with massive parallel machines. The Cray 3 machine, that was a single CPU machine. They built just one of them. It was too expensive. So there they use gold and arsenium and whatever for the transistors to speed it up. But no, it was unpractical. So now massive parallel machines have taken over completely. Hopefully one day they will create a CPU that's based on light, not electricity. Then you can speed up the frequency a lot without melting the entire CPU. But they haven't succeeded so far. Hopefully they get there. And I know they are playing around with crystals in memory, so you switch the spin of a single molecule, plus or minus, as a 0 or 1. Then you can have a lot of memory in a little crystal you can't even see with the eyes. So we will get there, but it's going to take time. We had one Japanese guy, Kuwahara. He was sort of a legend in the community in the early days of DNS. He claimed that he could do a DNS for complex simulation around cars, the wind around cars, and then he should design then drag reduction and stuff like that. And the scientific community didn't believe it. It wasn't possible. We didn't have computers big enough to do that at the time. And also the Reynolds number was way too high. I mean, the airflow around a car, that's pretty high Reynolds number. But the Japanese industry, they loved this guy because, I mean, he produced quite decent results. And then well, actually they gave him, I think he had 4 supercomputers in his home, in the garage, in the basement, and the PhD students coming and going all the time. So he was special, that guy. But it turned out that he was using, he claimed it was a DNS, but he used a third order method where the truncation error operated as a subgrid scale model. So finally, in the end, he had to admit, okay, it is not a DNS, it is an LAS. But the results were actually quite decent. And that's also something that is bothering me. People are doing 2-dimensional simulations and call it LAS and DNS. And they actually do steady state simulations and call it DNS and LAS. So in my ears, that's blasphemy. Sadly, they get quite good results, so I don't like it. And we can't really explain why. But I mean, they cover a lot of the physics actually by cheating. Of course, they should be shot, but we can't really do that, can we? Okay, any questions to DNS, LAS? It's a big chapter, this different LAS and the different subgrid scale models, the philosophy behind it, filtering the Navier-Stokes, stuff like that. I won't go into the detail. If you are going to play around with it, you have to be prepared to do a lot of reading. It's a big topic. DNS is actually much easier, just a Navier-Stokes. End of story. Very easy. Okay, we take a break and then it's verification and validation.